All right. Tonight's speaker is John Moretti. John studies vertebrate paleontology in the Jackson School of Geosciences at the University of Texas at Austin. His research seeks to document natural history and investigate patterns of changes in the animal community of North America over the last 3 million years. He explores caves across the Edwards Plateau of Texas to obtain new evidence on how animal communities change over time and how changes in the past led to the biodiversity of today. I started talking to John about presenting to our group in October 2024. So I'm really excited for tonight's presentation. And with that, I'm going to turn it over to John.
I got to
John, I
unmute.
think.
Thank you, Catherine. That was a lovely introduction, and thank you for inviting me to come talk to this group. I'm excited to meet with you all. It's certainly the first time I've talked to a group about paleontology in Illinois. So this is a new region I get to reach tonight, and I think it'll be a lot of fun. That was a great introduction. I have little to add. I am a paleontologist. I actually just finished my PhD work at the University of Texas at Austin. It's so recent, I keep forgetting to update this slide. I'm not a candidate anymore, thank goodness. I've moved slightly ahead in life, I guess.
Congratulations, that's a lot of work.
Thank you so much. And so what I wanted to do tonight was talk about some of my dissertation work, introduce you to some of the research I do here in Central Texas, and at the same time, introduce you to what we think, in a general way, we know about the Ice Age in Central Texas and in Texas more broadly. So we'll talk today about some new results, and we'll also talk just generally about neat caves, neat past animals, and neat paleontology work here in Central Texas. So let's get started. There we go. Let's get started. So I study the Ice Age, the Pleistocene, the time period that we usually think of as the Ice Age, characterized by these huge glacial ice sheets across the northern hemisphere, and these extinct, exotic, charismatic animals like these woolly mammoths that you see on the right. This time that we think of as the Ice Ages is a formal geologic period of time. It's the Pleistocene epoch. And a lot of my research focuses on the Pleistocene. And really, I'm interested in the Pleistocene because I want to know more about the animals that live around us today. So here in Central Texas, why do we have rattlesnakes and red-tailed hawks and roadrunners and not mammoths and saber-tooth cats or any other set of animals for that matter? And the Pleistocene, the Ice Age, can help us understand the animal community of the present day because the Pleistocene is this period of time that immediately precedes the time interval we're in today. So we can look at this time chart here on the right, at the left. And we can see that the late Pleistocene spans from about 125,000 years ago to about 12,000 years ago, and is succeeded by this time interval called the Holocene. That's where we are today, right? So the late Pleistocene, this latter portion of the Ice Age, is the chapter of Earth history that immediately precedes the time period we're in today, and the time period where humans really come to dominate the natural world. And so if we're interested in how things came to be, in why is the present natural world the way it is, it makes a lot of sense to look into the past, into this immediate past, for some clues, for some answers. And one thing I want you to note and think about tonight, we're going to talk about a little bit, is that the late Pleistocene is fairly long. It's over 100,000 years. And these glacial ice sheets that characterize the late Pleistocene and really characterize the entire Ice Age, the entire Pleistocene, Those ice sheets are not static through time. Global climate changes throughout the past 2.5 million years, throughout the entire Pleistocene. And these glacial ice sheets respond to that. And they wax and wane. I think people in Illinois understand this better than people in Texas, or at least that's my assumption. These glaciers waxed and waned in size over time. They were relatively small in warm periods, these interglacial and interstadial intervals that you see labeled on this time chart. And those glaciers were at their maximum extent during cold intervals, these glacial intervals that you see labeled on this time chart. And we can think about that visually too, right? We can look at these glacial ice sheets. Their size and distribution through time has been documented through multiple lines of evidence. And you can see here an example of waxing and waning, right? Kind of the smallest the ice sheets get during this last interglacial interval, and the biggest they get during this last glacial interval. In central Texas, we never saw these glaciers, right? These glaciers never went further south than the southern border of Nebraska or the northern corner of Kansas. But in central Texas, we actually know a lot about this last glacial interval of the late Pleistocene. And here in central Texas, we can find evidence of the late Pleistocene, and especially this last glacial interval, in caves. And on your left, you can see paleontologist Grayson Mead sitting in a cave here in central Texas, just north of San Antonio. And in front of him is a nearly complete skeleton of a saber-tooth cat. This is a very famous cave that produced many skeletons of such cats. That site, Friesenhahn Cave, is one of 17 here on the Edwards Plateau of central Texas that you see labeled in the map on the right. So we have here in central Texas on the Edwards Plateau, this big limestone formation in the middle of the state. We have pretty good coverage of the late Pleistocene. There are 17 sites that date to the late Pleistocene and have been sampled and studied by paleontologists over the latter portion of the 20th century. 16 of those sites are caves, like the one you see on the left. This is actually pretty dense sampling for any region, really, in anywhere in the Western Hemisphere. 16, 17 sites in one region. And this density of sites and the prolific nature of these sites, like Friesenhahn Cave, has led to the Ice Age record of Central Texas. It led that record to become globally influential. This record was influential in helping frame the international debate over what happened to the mammoths and the saber-toothed cats at the end of the Ice Age. Why did they go extinct? When did they go extinct? The fossils from these caves here in central Texas were pivotal in helping shape that debate, that ongoing debate. But these 17 sites, as impressive and as important as they are all younger than 20,000 years ago. They all fit between 20,000 years ago and about 12,000 years ago. They all fall within this last glacial interval of the late Pleistocene. And that's really fun because this is the dramatic end to the late Pleistocene. Our own species enters the continent. The glaciers that define this entire geologic epoch fade and collapse, leading towards the present day conditions. Global climate is changing, right? Driving that changes in the glacial ice sheets. And at the end of it all, these animals, like what we see on the left, these saber-toothed cats, these mammoths, mastodons, giant ground sloths, are all extinct. That is a really important interval to document, but here in central Texas, we have no known record of these earlier portions of the late Pleistocene. We know nothing about these earlier warm intervals, either interstadial MIS3 or interglacial MIS5. We know nothing about this earlier glacial interval. And so here we're kind of left with knowing how the whole story ends, but not knowing how did we get to that point? What set up these dramatic changes that occurred at the end of the Ice Age? And without evidence of these earlier intervals, we also don't understand how these global climatic changes between warm intervals and cold intervals, we don't understand how those changes affected regional ecosystems and regional animals. So if we could better understand these earlier intervals, it would shed light on what happens at the end of the Pleistocene and help us better understand the transition towards the present day. Why are things the way they are? And so that brings us to one of the caves that we're going to talk about this evening. That's Inner Space Cavern. This is a show cave today, a commercial show cave here in Central Texas. You can go visit it, and I hope you will if you're ever in the region. This cave was discovered in 1963, and you can see the initial part of the discovery in the photograph there on the right. This cave is right next to our Interstate 35, I-35. It's a huge interstate that runs through Texas. And at this spot, there was a railroad track. So in 1963, they're preparing to build this highway and preparing to build an overpass to allow traffic to bypass the railroad track. But this is a region that's known for caves, right? It's entirely limestone. And so the Texas Highway Department is going through and with a coring rig, drilling holes into the limestone to make sure there's actually enough bedrock to support all of this concrete and vehicles that are eventually going to be put on top of it. And believe it or not, well, they ran into a cave. And initially, they're drilling these 8-inch wide to 10-inch wide core holes. They hit a cave. There's no surface expression of a cave here. They've just discovered a new cave that nobody knew existed. And so what they're doing in the photo on the right is they've actually widened one of those small core holes to be 2 feet wide. And they called the state geologist working for the Texas Highway Department. His name was Jim Sansom. Jim came out and actually held on to the drill rod, wrapped himself around it, and they lowered him down. They knew how far, right? It was going to be 35 feet because they'd already collected these cores. They knew he was going to go through 35 feet of limestone and into a cave, but that's all anybody knew. So they lower him down this 2 foot wide hole, and Jim Sansom is such a good geologist that he actually has the presence of mind to have his headlamp on, and he's got his little notepad. So he's actually being lowered down in this small little hole, wide enough just for his shoulders, and he's taking notes on the bedrock as he goes through it. And he pops out into this, one of the biggest, most beautiful rooms in the entire cave system. And you can see they start to map and survey this room. There is no surface expression to this cave. This is just ranch land. There's no cave entrance. No one knew there was a cave here. And so as they're working in the cave here in 1963, they actually become short of breath repeatedly and have to return to the surface. The air has very little oxygen in it. And they're taking photos and documenting this space. And they're using these old flash bulbs that would put off a little puff of blue-gray smoke. And the smoke would just sit. It wouldn't blow away. It wouldn't dissipate. It wouldn't move. There was no entrance. There was no connection to the surface other than these holes they just made. But that is just the start of our story, because later these cavers, or sorry, these Texas highway workers who drilled into the cave and the geologists who'd entered were just the first people to enter the cave. They left, right, to do what they needed to do to prepare for the highway, which they eventually built. This was enough bedrock after all. It ended up, the highway came in anyway. But in the meantime, they left a hole on the surface, and word got out. Word got out to teenagers here in Central Texas who were starting to develop one form of North American caving. So they would grab rope from their dad's barns, tie it to car bumpers, and lower themselves in. And they started mapping the cave system. Cavers came from Dallas, a few hours away, and also contributed to this effort. And they discovered fossil bones, Ice Age animal bones, throughout the cave system in many different locations. And so they called the man you see in the photograph here in the center, that's Bob Slaughter. He was a paleontologist at Southern Methodist University in Dallas, Texas. He and a team came down later in 1963, and they were so excited about the potential for discovery here. They were so excited that they came down late at night, I think on a Friday, and camped on this ranch land. And Bob Slaughter writes that they all woke up early because they were excited, like that Christmas morning sort of feeling. And they sat around a campfire making coffee in the morning, all staring at the landowner's house, waiting for the lights to come on so they could walk over, introduce themselves, and say, "Hi, we'd like to go in your cave and collect some fossils." Bob Slaughter did that and collected quite a sample, and then returned to Dallas. He didn't ever come back and pursue this investigation any further. But later, a year or so later, the man you see on the right, this is Ernie Lindelius, a paleontologist here at the University of Texas. He and his grad students started working in the cave and taught us most of what we know about the Ice Age record in Inner Space Cavern. What Ernie showed us was that the fossils in the cave are concentrated in 4 different locations. They're concentrated in places that look like this. What we're looking at is a huge mound of rubble. This is a 16-meter tall, 25-meter wide talus cone. It's a mound of limestone boulders and gravel and clay. These talus cones formed beneath sinkholes that opened into the cave. So we have holes opening into the cave from the surface, right? This is what the highway department was worried about. If they put something too heavy on top, there may not be enough ground underneath to support it, and you may have a sinkhole. Well, this was happening in the past. And what we're looking at here is sort of a time capsule. This is a mound of rubble that accumulated in the cave, and it accumulated and accumulated and accumulated beneath this vertical shaft to the point that it closed the shaft. It closed the entrance. And then that entrance, that former sinkhole, was grown over with vegetation and trees to the point that in 1963, nobody ever knew that there was a cave here, let alone sinkholes. So there are 4 of these, what we call debris cones throughout Inner Space Cavern. And each of them contains abundant, rich quantities of Ice Age fossils from many different animals and all different sizes, mammoths all the way down to tiny toads and mice. So this tells us that this cave was open periodically throughout the late Pleistocene. Here's another look at a different debris cone, this one largely covered in speleothems, in cave formations. And what's really exciting about this cave is that not only were the fossils abundant and representing many different species, Ernie showed, or Ernie obtained a set of evidence that suggested that these sinkholes into the cave may not have been open all at the same time. What Ernie found was different animals, different fossil species in different debris cones. He obtained 3 radiocarbon ages, one on each of 3 different debris cones, and those ages were different. And so his hypothesis at the end of his work was that these debris cones may have formed asynchronously throughout the late Pleistocene. They may not have all been open at the same time, the sinkholes. And so that creates the potential that these huge mounds, right? 25 meters wide, 16 meters tall, each one may record millennia of, of Earth history. And if they don't all record the same interval of time, right, they may be different chapters to one book, and we may be able to stack them together and form a composite record that documents much more of the late Pleistocene than we've ever seen here in Central Texas. That was the hypothesis. It was really exciting, the potential, but that's where his work ended, and nobody had returned. So grad students, well, everybody visits this cave, right? From kindergartners to senior living facilities, everybody takes field trips to Inner Space Cavern, including incoming PhD students. So this was one of the first places that I visited in Central Texas when I moved here for my PhD. And I realized the potential here at Inner Space Cavern. I realized the importance of what Ernie had set up for us and what might be preserved. But I also realized that Ernie's hypothesis was very unclear. We still had a lot of unknowns. And we needed more evidence to actually determine if what he thought was in this cave, the record that was there, was actually what he thought it was. And so as part of my dissertation, I set out to explore and examine the fossil animals in these debris cones and try to date these sediments in a more intensive way so we could get at, was Ernie right? So tonight we're going to talk about some of the animals that Ernie and I have discovered in this cave, and then we're going to talk about new lines of evidence that I was able to obtain that helped me clarify what is preserved in terms of a record of the past, a record of Earth history in this cave. So first of all, I think we have to start off with just thinking about, well, how did these animal remains get into this cave in the first place? And at the cave itself, in the lobby, they have this mural that you see on the left as an example of animals falling into the cave, right? I especially love this mammoth with the saber-tooth cat riding on its back, right? As it tries to eat its potential prey. That is probably unrealistic, right? Entire animals are not falling into this cave. But we do have remains of mammoths, saber-tooth cats, all of the things that you see there on the left. But the way the bones of these animals are entering Inner Space Cavern is in a much more mundane manner. So these big animals, most of them are better thought about in the form of the skeleton that you see there on the bottom right. This is right, these animals are living and dying on the surface. That's normal daily life in the natural world, right? And then when they die, scavengers consume portions of them, insects colonize their bodies, right? Wind and rain, the elements take their toll. And over time, the soft tissue goes away and the bones, the individual bones in our bodies, can become free from each other, from their constraints in their life. and they can move. Right? So these bones, individual bones, can be picked up by water, by wind, by other creatures, and be washed, be blown, fall, be kicked, thrown into these sinkholes. Right? This, you can think about these sinkholes as acting a lot like storm drains. And they're, especially flowing water, can move objects into these drains. So big animals are really are really living and dying on the surface, and bits of their bodies are entering the cave. We don't find whole skeletons of pretty much any of these large animals. I say pretty much any because there are a few exceptions. In the case of jaguar remains and a couple other animals, animals that at least in the present day have a proclivity or a tendency to live in caves, to use caves as shelter, right? And you could imagine those animals potentially dying in these shelters that they're residing in, right? Dying at home. So in those cases, we do get whole skeletons, but it's very rare. There are also many small animals, right, that we find as fossils in Inner Space Cavern, and the remains of those animals are entering the cave in an even more mundane manner. Something like the photo you see there in the top right. And this is a naturalist group. You guys are familiar with owl pellets. That's what's happening in the photo on the right, right? And owls like to roost often along cliff edges, and these sinkholes would have been cliff edge-like, right? So if we have these owls, they're roosting generation after generation, regurgitating the remains of their prey nightly into the cave. We can accumulate a great number and a great diversity of small animals over time. And of course, bats, we have a lot of bat fossils, and those are animals that are perfectly happy living in caves, coming back and forth, and they're dying at home too, right? So there's multiple ways we can accumulate a fossil assemblage like what we see in Inner Space Cavern. It's really not like this mural that we see on the left, as fun as it is. It's much more mundane, really kind of boring, and takes a long time to accumulate bits and pieces of many different species. So with that understanding behind us, we can look at some of the animals that do occur as fossils in this cave. And we'll start off with a giant armadillo. So in each of these slides, I'm going to show you a fossil from Inner Space Cavern on the right, and I'm going to show you what these animals may have looked like in an image on the left. And on the left here, you can see two armadillos. The living species is the one there on the bottom. It's this smaller one. That's the 9-banded armadillo. I don't think they make it up to Illinois, but we certainly have them in abundance here in Texas. And next to him is this extinct, beautiful armadillo, it's called. That's actually its name. This was really a giant armadillo, up to 5 feet long. A huge thing. We would avoid hitting it with our car, right? We should avoid hitting the 9-banded, but nobody's going to voluntarily run into this much larger extinct Ice Age armadillo. And what we're looking at on the right is a piece of the carapace, the armor that forms the shell over these armadillos, right? That shell is made up of many hundreds of bones, like this one you see on the right. And as those animals die and decompose, their shell can come apart into those individual osteoderms, those bony armor pieces. So we find these beautiful armadillos. We also find a larger relative of the armadillo, Glyptodont. You can see there the beautiful armadillo next to the Glyptodont for scale. These Glyptodonts were quite large, weighing up to something estimated like 1,200 pounds. And those shells reaching 3 or 4 feet tall on their backs. These were huge animals. But like armadillos, they're close relatives. Those shells are made up of pieces of bony armor, like you see there on the right, and that's what has been discovered in Inner Space Cavern. And this is one of the more interesting animals from the cave. Like present-day armadillos, glyptodonts have a very limited distribution as fossils. That suggests a similar limited distribution to what we see in present-day armadillos. And this is the only record of a glyptodont on the entire Edwards Plateau of Central Texas. This is really the only record from Central Texas, and it's one of the westernmost occurrences. It's almost is the westernmost occurrence, it's close, of these animals in the late Pleistocene. So there's a clue here that inner space is allowing us to see that can help us think about the ecology of this animal and its distribution across the southern United States. We don't fully understand what that means, but this record is really important both for the region and for understanding these animals in North America more broadly. A really exciting fossil find here. I was hoping to catch these animals again, but I didn't come up with any more of these creatures in my excavations. It was disappointing. But we're lucky that Ernie caught it. And these are both, we think about glyptodonts and armadillos as being neotropical, right? These animals are more abundant, more diverse, more widespread, both in the past and the present in South and Central America. And they make it up into the present-day United States, but they have a real limited distribution, and there's usually only one or two species. And there's other neotropical species that we see in Inner Space Cavern as well. One of them is this spectacled bear. You can see a fossil, that brown fragment on the right is one of the fossils from Inner Space Cavern, next to a jaw from a modern spectacled bear, to give you some kind of context. And then on the left is a modern spectacled bear. These animals live in the mountains of South America in the Andes. But during the Ice Age, during the Pleistocene, there was a northern counterpart, this Florida spectacled bear. These animals, as you could imagine, are quite common in Florida, and they occur not uncommonly in present-day Mexico. But throughout the rest of the present-day United States, they're really uncommon as fossils. And during the late Pleistocene, they really don't occur far west. So that, again, this is a special record from Inner Space Cavern. This is the only known occurrence of spectacled bear on the Edwards Plateau throughout central Texas. And it's again one of the westernmost records of this species in North America. So again, these scraps, right? These bits that you, like that fossil that you see on the right there, they really are important. They can help us think about both the region and these species throughout their range. We have a lot of fossils of horses, right? These glyptodonts and spectacled bears are quite rare, even in Inner Space Cavern. But extinct horses were really widespread across North America and quite abundant. We find them in abundance in Inner Space Cavern. What you see on the left there is a incisor. This is a lower tooth, right? This is one of the teeth why you want to feed horses carrots with your hand out, because they have incisors on the top and bottom. That's an incisor, and they'll really bite your finger if they can't tell it's not a carrot. I know from experience. So these horses were quite common throughout the late Pleistocene. I think they're charismatic animals, but they become kind of routine finds because we do find them often throughout North America. And again, I think this is a useful opportunity to remind folks that horses did start out in North America 55 million years ago. They went extinct here at the end of the Ice Age, but they persisted in the rest of the world. Why? They persisted long enough that the species that we eventually domesticated, right, the Spanish ended up bringing it back to their ancestral homeland. So both parts are true. The Spanish did bring horses to North America, but they also started out here. And understanding why they went extinct, right, kind of will be kind of the finale to writing that story of these interesting animals that have become so important to us. And of course, we're in a cave. We're finding a lot of fossils of bats. And what's exciting is we find many different bats. Today, bats are quite uncommon in the cave, but during the Ice Age, this was a hot spot. This was a widely used uh, shelter for many different bat species. At least four different species of bats lived in inner space during the Pleistocene, during the Ice Age. The most abundant in Inner Space Cavern, and perhaps the most interesting, is this Brazilian free-tailed bat that you see in the photograph on the left and that you see a skull of there on the right. These bats form the largest colony of any bat species in the world, and they do so here on the Edwards Plateau of Central Texas. In a handful of caves here in Central Texas, these bats form colonies that number up to 15 to 20 million individuals in single caves. It's enormous numbers of bats. And I should have written it down. I always have this statistic when I don't need it, and forget it when I do, but they eat just outrageous quantities of insects every night. In large part because these huge colonies are nursery colonies, they're maternity colonies. They're occupied by females who have migrated into the region pregnant, and they're spending the summers here giving birth and raising pups. So they're consuming gigantic quantities of energy and eating a lot of insects. They're eating so many insects that they are controlling the regional ecosystem from the ground up. Not only on the surface, but in the caves too, because they return to the caves and guess what they do? They poop, right? All of that guano then provides an energy source to these cave systems, right, that don't receive sunlight. This is the basis for primary productivity in these caves. Not only are they controlling regional ecosystems by eating all of these insects, especially moths, which they love apparently, they are making possible our agricultural activities throughout Texas, right? They are controlling species that would otherwise be enormous and uncontrollable pests on our agricultural farms and produce stands. So these species are really important, but we don't know very much. We know very little about their natural history, both in Texas and across North America. Because even though they occur in such abundance, they're actually very rare as fossils. But here in Inner Space Cavern, we actually have the oldest record of this species, the Brazilian free-tailed bat, dating back to the, well, you'll see the dates in a little bit. We have the oldest record of this species, and these fossils occur in an extraordinary abundance in two sites in the cave. And so these fossils actually, as we establish a better understanding of the chronology of the cave and the foundations of the record here, these fossils are going to reveal, or have the potential to reveal, new insights into the natural history of this species and help us understand how long they've been playing this critical role in the ecosystems here in Central Texas. So really exciting story to be told by these fossils if we can establish a chronology that tells us when these bats were here and how long and so on. From bats to a giant ground sloth, right? Tiny to big. This is Jefferson's ground sloth. This was actually named for our president, Thomas Jefferson. He studied fossils of this animal. These animals are pretty widespread across North America as fossils, especially eastern North America. But here in Central Texas, they're exceedingly rare. There's only one other cave that has any fossils of this animal, and we don't really understand the age of that cave yet. But here, in Inner Space Cavern, we're catching this, what is otherwise a regionally rare animal. They're big, they're charismatic, and I think the fossil that I'm showing you here on the right, here's a highlight so you can hone in on what we're looking at, really illustrates nicely the rather mundane nature of fossils in this cave. This is most of what paleontology looks like. You guys know that. I heard you talk about collecting there at the start. You know, right? We're not often, rarely ever finding beautiful, perfectly preserved whole skeletons. What we are almost always finding are these bits and pieces, right? And so what you're looking at there on the right is a tooth, a partial tooth. It's an ugly tooth. We'll look at it again later. But it's enough evidence, right? We have a couple other scraps of this animal, and those little scraps, those bits and pieces, become so important. And we have a range of carnivores, too, who occur as fossils in the cave. Here we have a jaguar, right? That's a modern jaguar on the left, and a fossil jaguar on the right, but these are the same species. We've confirmed that more recently with ancient DNA studies that clearly show these jaguars that were widespread across North America during the Pleistocene are the same species that live in Central and South America today, the same species that we pushed out of Texas actually in the 20th century. But these Ice Age fossils were bigger. These Ice Age jaguars were the size of modern day lions, so quite a bit bigger than the living species in Central and South America today. And this is one of the only animals that we encounter in Inner Space Cavern as partial or complete skeletons. And there's actually two individual nearly complete jaguar skeletons from different ends of this cave system. Really exciting finds. And this is an animal that may have been sheltering in the cave, and that's why we're finding these partial skeletons. Jaguars in Central and South America today do use caves as shelters and as dens. And so it's a fun thing to think about as we pass through this cave today as a tourist or as a paleontologist, to think about jaguars lurking around the corner 15, 20,000 years ago. And another living species, the prairie dog. I really like highlighting the prairie dog and this next animal, the white-tailed deer, because they're so familiar. But these animals were living during the Ice Age alongside that Jefferson's ground sloth, alongside mammoths, alongside saber-toothed cats, all of these exotic kind of foreign animals to us today. And these animals highlight the differential survival through the late Pleistocene. Some animals were able to persist through the changes that occurred at the end of the Ice Age. Some animals were not. And we don't fully understand why, but that understanding would be really valuable, especially as we move through another interval of humans spreading, becoming more abundant, becoming more influential, and another episode of climate change, right? We could help predict the future if we understood why these past outcomes occurred. We could think about future outcomes. Those white-tailed deer were undoubtedly worried about coming across this saber-toothed cat. This is the same species that we saw laid out as a skeleton early in the talk with Grayson Mead sitting behind it. But in Inner Space Cavern, we don't have a whole skeleton. The only fossil discovered in this cave of this species is the tooth that you see there on the right, an incomplete, very tiny tooth. You see the scale bar. This is actually a lower canine of a cub. This is a baby tooth. This is a deciduous milk tooth. So one little tooth, right? But it's enough to establish the presence of this species, and even more, it tells a little bit of a story, right? There was a cub around this cave at some point during the Ice Age. Really interesting, a really special specimen there. And then the last animal we're gonna look at here is a peccary. You might be familiar with the javelinas or peccaries of the arid Southwest or Central and South America today. These, there were peccaries during the Ice Age too, but we had larger species in North America then. And what we find in Inner Space Cavern are flat-headed peccaries. You can see an illustration of one of these animals on the left. And then inset, you can see that animal in scale next to a human. They're pretty large and they're much longer legged, less stocky than the living peccaries of Western Texas and Arizona and New Mexico. These are the most common large animal in Inner Space Cavern. And you can get a sense of that from the photo on the right, this cluster of skulls. There was a photo of Bob Slaughter earlier in the talk. He's carrying a skull as he scooted through the cave on his belly. That was another one of these skulls. We find whole skeletons of these animals throughout the cave. And that's actually fairly common throughout Eastern North America. These animals show up in abundance and as whole or partial skeletons in caves. And again, like the jaguar, this appears to be an animal that was willing to use caves as shelters. And over time, there were a lot of peccary carcasses accumulated in Inner Space Cavern. We find them in each of the debris cones, really everywhere you look in this cave, there's flat-headed peccary bones. So that's kind of a limited look at our cast of characters, right? We'd be here for hours if I went through everything, and you'd probably get pretty bored once we got to the mice and lizards. I honestly would get a little bored too. But what makes all of these animals more interesting is their distribution in time, right? When were these animals present? And how far does this record of Inner Space Cavern go back? How far does it reach into the past? Well, we're going to look at a more technical, slightly more technical slide now. And what I'm showing you here are just idealized stratigraphic profiles for 3 sites in Inner Space Cavern. They're very simple, right? These rectangles simply show you different strata, different depositional layers at 3 different sites. Those sites are labeled there across the top of the chart. And in these columns, you can see black dots. Those are radiocarbon ages I obtained at these 3 sites. To the left of those black dots, you can see a date. That's the date that resulted from those radiocarbon ages. And you can see a material, snail shells, organic sediment, charcoal, bone, tooth enamel. Those are the materials that those dates were based on. On the right are interesting specimen occurrences, those blue dots. We can ignore those for the time being. And what I want you to look at is that in both debris cone 2 and debris cone 3, these lower depositional units, these lower layers, deposits, extend back to the upper 40s, 40,000 years ago. And those lower depositional units fall within a time period that we refer to as marine isotope stage 3. It's the last interstadial. It's a last warm period prior to this last glacial interval that we know so well from the rest of the region. So these lower depositional units in both of those debris cones actually date to a time period that we had not previously sampled here in Central Texas, right? It gets us out of that last glacial interval and into a warm interval. And you can see this site called Bat Breakdown in the middle also fits within marine isotope stage 3, this warm interstadial interval that spans from about 29,000 years ago to 57,000 years ago. So then these upper depositional units in both debris cone 2 and 3, they date to this time period that we're familiar with on the Edwards Plateau, the last glacial interval 20,000 years ago to 12,000 years ago. And it appears that debris cone 2 extends a little bit into the early Holocene with that 9,500 year date there at the top. So what this chronology that I was able to obtain, at least for these three sites, shows us is that not only are we looking at portions of this last glacial interval, MIS2, but also portions of this last interstadial interval, this warm interval. So it reveals that these debris cones do contain a very long record of the late Pleistocene, that it does extend further back in time than any other known regional late Pleistocene site. But it turns out that these debris cones are actually contemporaneous. They formed more or less synchronously throughout this time interval. They don't record all of the same time, but they do overlap broadly in time. And Ernie got the sense that they were different by sampling at different deposits in different debris cones. And so sampling different intervals and then extrapolating that most of that debris cone represented some near contemporaneous portion of time. So we actually do have a very long record, a record that is longer and extends further back into the late Pleistocene than any other regional site. But it turns out that may be the case for all four debris cones in the cave. They may be contemporaneous after all. So Ernie was right in many ways. So then we can ask, okay, we have this chronology and we know that these sites span a climatic transition from warm to cold. Did that affect the animals at all? Well, that's a tough question to get at, but we have a little bit of evidence to think about. Most of the animals that we talked about are found throughout the time represented in these debris cones. And that's especially the case for these beautiful armadillos and these Brazilian free-tailed bats. It seems that they are present throughout the warm interval and the cold interval, the interstadial and the glacial interval. Their fossils extend vertically through those times. That's not the case. Although that's the case for most animals in the cave, it's not the case for this Megalonyx ground sloth and for these large extinct pronghorn, which I didn't actually talk about. That was a real mistake. But one animal we're finding in the cave are these pronghorn. You may know pronghorn from drives through Western North America. A lot of people refer to them as antelope. They're not antelope. They're North American endemics, unique to this continent. And there's only one species today, but in the Ice Age there were quite a few. And so we're not sure what species we're finding in Inner Space Cavern, but we're finding some large extinct species of pronghorn. Both these pronghorn and the ground sloth occur as fossils in Inner Space Cavern only in deposits that are older than 20,000 years ago, that predate the last glacial interval. And if we look across the rest of the Edwards Plateau, Megalonyx occurs in only one other cave site. In that cave, we don't understand the age of. It's quite enigmatic. And pronghorn occur in only one other cave site. And that cave site is far to the southwest, almost in a different climatic and ecological settings. It's so removed from the rest of the plateau. And so it appears that this pattern that we see in Inner Space Cavern of these two species occurring only prior to 20,000 years ago, prior to the rest of the regional record, may be reflecting a broader regional pattern, suggesting that these animals are absent in this last glacial interval. And that's why we haven't picked them up ever in virtually any of the other 16 cave sites. So we have a hint that this climatic transition may be influencing the animal community, but not on a large scale. It may be affecting one or two species, but this transition appears to have been something that most species could navigate and handle both the warm temperatures and the colder conditions. So this gives us some evidence to start thinking about how that climatic transition affected regional ecosystems in animals. It gives us a basis for it. And this regional chronology allows us to start posing more interesting, more detailed questions about the natural history of Central Texas and really Western North America using Inner Space Cavern as a case study. And in doing so, we can get at bigger picture questions about how and why animal communities change over time and what drives those changes, how rapidly do those changes occur, really getting at questions about how nature works, right? These sorts of sites allow us to explore those sorts of questions that, of course, then lead us to a better understanding of our past and our present and help us or give us the knowledge to be able to predict future outcomes in the natural world. So really valuable record, and I think we're starting to gain a greater resolution on this natural record thanks to some new work and some old work too from paleontologists, both me and former. So I'm going to stop there. I want to thank these institutions that you see as logos on the left who supported my work financially or otherwise. And I want to again thank everybody for coming out tonight, for listening to the talk. I want to thank Catherine for inviting me, and I hope we can have some questions and a brief chat about what the heck all this means. Thanks, everybody.
I want you to continue on for several more hours and
Me too.
answer these questions.
Well, I do too, but it's not always right. Some of these questions we just can't get at yet. They're generational.
Well, I got a dozen questions, but I'll let other people go first because everybody knows I have a lot of questions. Shall I start?
Oh, I do have a question. So first of all, when you started talking about the colonies of bats and you said 15 to 20, I thought you were going to say 1,000, and then when you said million, I was just that was a cool moment. I I did not think it was going to be that scale. So that was neat. I'm curious about the sinkholes that formed and the two that you talked about. How far apart geographically are those two? You said they likely existed at the same time. Were they close to each other, a mile away? How far geographically?
That's good. That's a good question. It's a big cave, so it's the fifth longest in Texas. But I think that means it's only a handful of kilometers. It's
Okay.
not gigantic, right?
Yeah.
And these two debris cones, at least the faces that we can access of these debris cones, at their closest, they're 90 meters apart.
Okay. So
So
relatively close.
you can see them, right?
Yeah.
You can see one from the other. Bats could have flown in one and out the other.
Sure.
Yeah.
Oh, cool.
But one thing we don't understand is the shape of these entrances and how they would have appeared, right? Whether they were huge and chasmy and you could have driven a truck into, or they are just narrow shafts. We don't understand much about that.
Sure. Okay. Thank you. Thank you. Fascinating presentation. Thank you so much.
Thanks, Chris.
So I have a question on the fossil record. There's no evidence going back to you referenced Miss 2 and 3, but there's no fossil record for 4 and 5.
That's correct. That's correct. Yeah.
How do they explain that there's no fossil record for those time periods?
Good. Right as we move back further into Ice Age, sites become more scarce, right? There's more time for these things to be destroyed. But we do have sites, certainly of MIS 5, this last interglacial period in eastern Texas, and in southern Texas along the Gulf Coast.
Hmm.
But we don't have any here on the Edwards Plateau, and nobody has been pressed to explain that. But I've started to get into that position now. And I'm working in caves throughout the region. And what the explanation that I start to understand, the way I start to understand this problem, is that we have a changing landscape and a different landscape during the Ice Age, right? We have prairie dogs. Prairie dogs live in burrows. Today, we have a soil on the Edwards Plateau that's about a couple inches thick. Prairie dogs live in habitats with at least a meter of sediment, of soil, right? And there are multiple lines of evidence that suggest there was that and more during the Ice Age. And then limestone itself is very, right, easily eroded. And so these caves, I think, are shifting over time in how they're connected to the surface as a result of these landscape level changes. And the cave has to be open to the surface to receive any, right, remains from that time period, receive animal remains or anything else. And so it seems that caves that were open during that interval, well, first of all, it's possible that we simply didn't have many caves that were open to the surface during that interval of time. I think that's unlikely. So we have two other options then, two other prominent options at least. First, it's possible that some of these caves that we know today and have been in had materials that dated to, 100,000 years ago or so within that last interglacial interval. But since then, the caves have been cleaned out in part, right, by erosion. And that record was destroyed, right? That's possible. It's also possible simply that there are sites of that age and we have not found them or we have not recognized them for what they are.
So that was my next question is, are there instruments, because they obviously didn't know this cave was there until they started doing the boreholes. Is there equipment that can now find other hidden caves that may exist?
Yes, and we could do that, but we could spend the rest of our lives doing that, right? And we could spend the rest of our lives and not find any other fossils. This region is so cave rich that we could get a million hits and never, right, find that needle we're looking for. But what we can do that's actually more practical is, right, this cave, this was actually the first cave I was ever in and first cave I ever worked in, but it led me to become familiar and even to join the local caving community. And so now I have access to show caves and wild caves. And I have access to a network of people who encounter these things, including people who get called when construction of any kind encounters a cave nobody knew was there, right? And all of these people now know what I do, why I do it, and what they might find that could be interesting to me, right? So I have this network of sort of spies out there looking for these very things, which is both cheaper and a little bit more practical method of trying to find that. And I think eventually we're going to come across it. During the 1960s, construction encountered two caves here in central Austin that date to the Middle Pleistocene, over 780,000 years ago. There's no other cave in the region that dates that old. So that discovery really tells you that there's way more of a record here, and we're gonna bump into it eventually. And I've tried to set myself up so that when we do bump into it, somebody calls me.
So, question: a lot of the animals you're talking about seem to connect more to South America, and what we know from like the Brazilian bats and some of the other ones. so my question is, we know the horses migrated up north. Are these animals migrating from South America up, or are they being pushed down to South America?
Oh.
And is there an equal migration?
Oh man, that's a great question.
Thank you.
Well, I think first of all, it's important to note that in whatever direction this is happening, it's dispersal. Dispersal is different from migration because it's not a round trip, right? Migration is regular. You do it on a cycle and you go both ways.
All
Dispersal is one way, and that's what's happening with horses as they enter the old world through the Bering Land Bridge. That's what happens with mammoths and bison as they enter North America from the same land bridge. That's what we did to get to North America in the first place. We dispersed from Asia. And so, yeah, it's a similar process, just in a different direction. The Panamanian Isthmus, this little narrow strip of land right where the canal is, formed as land about 3.5 million years ago and provided a connection between North and South America. And guess what? Lots of animals started dispersing in both ways. And so that, for example, that spectacled bears started out in Europe and Asia, dispersed into North America. And then when this Panamanian Isthmus formed, some species dispersed into South America, where they speciated and we got this unique, distinct group of South American bears. And then some of those bears disperse back north. So we get the giant short-faced bear as a result, and its close sister, the spectacled bear. So if we look across time, it becomes in many directions, right? But as what we're really thinking about, and I think what you're getting at is, yes, the spectacled bear, the glyptodont, the armadillo, these are all animals whose ancestors dispersed north from South America and have reached, it seems, some climatic or ecological barrier that prevents them from moving much beyond the southern present day United States, right? That's what I was trying to get at, is these occurrences in inner space are actually really interesting because they start to show us where these animals could and couldn't live in the past.
Yeah. So I have another question. The bat guano, since there's a lot of bat guano in the caves, have you been able to look at any bat guano for the fossils in it?
That is something I hope to do in the future. The guano in these caves is not terribly well preserved in the sense that it's kind of a homogeneous organic mass, right? We can't pick out individual poops. We can't pick out insect skeletons as such. But so as macrofossils, they're not very interesting. But in terms of biomolecules, I think they can be very, very interesting. And especially in inner space, but especially in other regional caves too that have large quantities of guano. Because in these guano, we have the capabilities now, including here at the University of Texas in Austin, we have the capability to sample ancient DNA. We have the ability to sample it in a way that we don't have to target anything. We don't have to be looking for any specific species. We can shotgun it essentially and see what's in there. And if we do that, we should capture bats. We should capture what they were eating and then pooping out. Sorry. And then hopefully it's possible even that we can also capture, because they eat a lot of moths, right? And moths are pollinators. It's possible too then that pollen coating some of these moth bodies is actually still preserved, and we can capture some genetic information about what those moths were feeding on too. So we can start to get at a lot more of the ecosystem than is possible just as physical fossils.
And that
But
would be amazing because that would show you a lot of why the animals are there if you know the environment. Because right now, I'm
yeah,
taking you're not getting many um, floral, uh, you know, fossils there.
that's right. These alkaline cave systems are really bad for the preservation of plant macrofossils, and they probably have pollen, but the study of pollen itself as a fossil, as the morphology of the fossil is so specialized. There's so few experts working on pollen today that this has just never been studied to a great
Hmm.
extent, just in a couple caves. So if we could apply this, these DNA methods, we could access that exactly what you're saying. We could get at other aspects of these ecosystems.
It's fascinating. I well worth the wait. I'm just fascinated. So, if I understand correctly, the debris cones were formed when the ground, sinkhole, rocks fell in, and other things fell in. So, my question, are there quarries in the Edwards Plateau that you can see the layers looking at them, that the layers that fell in? So, could you see those layers in, like, if you went to a quarry in the Edwards Plateau?
Not that I am aware of. There are a couple quarries, um, and I'm sure they've eaten through caves. But Inner Space is a really large cave. Like I said, it's the fifth longest cave in Texas, and some of these rooms are really think about one of your basketball gyms in your local high school. Some of them are that big. And so in those sorts of caves, you have a high probability of sinkholes happening because these rooms are getting so big, they're eating away at the ceiling, and you're going to get these collapses, and then you can get these huge debris cones forming. But most caves just aren't like that. Most caves are smaller, and if some of these quarries have eaten through and made a cross section like you're talking about, have eaten through a big cave and had that cross section, it's either gone or they never told anybody it was there, or right, we're unaware of what's going on in these private facilities, I'm afraid, to a large extent.
Hmm.
Yeah, because actually, I'm from I used to live in that area, but that Texas Stone and Rock or whatever, there's a quarry that's just, you know, 5 miles down the road from that inner
Yeah,
space.
yeah, yeah. I look at
Yep.
that all the time and think, what was there?
Yes, I used to.
Ah, yeah.
And
If you got a quarry 5 miles away, that must drive you absolutely insane.
I try not to think about it.
Yeah.
Yeah.
And it's a huge quarry.
Oh,
It's
it's yeah.
acres and acres and acres of
Mm.
land. I mean, it's
And they
it's
don't
square
open it up
miles.
for anybody?
Not that I've the Austin Club had tried to get. Yeah, they won't let anybody in
Yeah.
there.
Hmm.
Yeah.
Can I
That's really
assume,
unfortunate.
that there was no or minimal water flow through the cave system between the time of deposition and
Mm.
today?
That's a great question. No, I think that's a reasonable assumption, but I we know that's not the case. Um, so in so I have two things to kind of comment on that. That's what I had hoped initially, because caves are great for the preservation of biomolecules, at least caves in central Texas. It's possible that these caves, because they're stable in terms of their moisture and temperature environments, it's quite possible that they regularly preserve, and they do regularly preserve, things like collagen, the protein in bones that we prefer for radiocarbon dating, and even ancient DNA. And so I went into this project assuming that we're going to be able to date things like directly, things like the glyptodon and the spectacled bear, these really important and special records and these animals that we don't have direct dates on really anywhere in North America. I thought I would build my chronology and also then pin down all these individual animals in time. And I wasn't able to because there is no collagen. There's no collagen in any of these bones throughout the cave. So I went on this huge radiocarbon program and destroyed a lot of fossils to find out there's simply not collagen preserved in these bones. But what is there is manganese and iron oxides in the bones. And we get those forming in caves, those materials forming in caves as the result of interactions between surface water and groundwater. And surface water, okay, great, that makes sense. We have these huge, potentially huge sinkholes. We certainly have openings to the surface and materials coming in. Water is going to come in too. It's a drain. But it turns out that during the 1990s, well, up until the 1990s, this cave would flood from below. The aquifer would actually flood up into these cave passages and make a lot of the tourist trails unpassable, at least for people that were willing to pay for it. And I knew that, but I had assumed that this wasn't a regular phenomenon in the past, further into geologic time, and that materials in these huge cones would have actually been safe from any sort of flooding, unless it was really frequent and it was a lot of water. But those results from the radiocarbon program, both the absence of collagen and the presence of these other materials that form through the interaction of groundwater and surface water, suggest to me that the cave was actually flooding quite regularly throughout the late Pleistocene, and that makes sense. The cave has stopped flooding since the 1990s, and since the 1990s, there's been a huge, enormous influx of humans into this part of central Texas, leading to an enormous strain on our water resources, right? We've got a lot more straws in the aquifer now. Yeah. And we've had a lot less favorable conditions. It's been a lot drier and warmer since the 1990s. And so if we go back into the past, we reconstruct the Pleistocene as cooler and wetter relative to the present day. And so all of these lines of evidence suggest to me, yeah, the cave was probably sumped fairly regularly and fairly deeply, enough that most of these fossils were actually interacting with that water, and the chemistry that resulted, was not favorable to paleontology.
Can I assume that the bones themselves have not absorbed much of the calcium carbonate from the formation of stalactites and such?
I hope so. But I don't assume that. I don't think we can safely assume that. Some of them have absorbed more than others. So there's one of these sites, actually the one Bob Slaughter visited, where the bone is, it sounds, looks, and feel like ceramic. There's nothing organic left, right? It has been totally replaced, I think, with calcium carbonate, calcite from the limestone. Most of the other sites are better preserved, but that's a huge problem, because then when I don't know how much calcite is in them, it's less than that other site, but I don't know how much. And so when we start to date bones and we're not using collagen, there's this resulting uncertainty of how much of that carbon that I'm dating is actually from the animal, how much of it is from the cave system. That leads to some ambiguity about my radiocarbon dates.
Yeah, can't rely on them.
Yep.
So I am not a fan of caves or underground. I think they're fascinating as long as somebody else is doing it, and I'm not the one going into the dark and all that. But it sounds like you're doing a little more caving than originally. So my question is, how many times you've got into an area where it's really scary or a little too tight for comfort?
Oh, often, regularly. Yeah.
Yeah.
Yeah, and I mean, a good example is I'm helping one project I'm involved in. We're mapping some new passages that were recently discovered in a long known cave. And so we just wrapped up a season of mapping there, and there were two. We're in uncharted territory. No, every step we take, no human has. But this past trip, it's hard, and we found two spots. We found the first spot we came to. This is a cave that has a stream flowing through it, and we come to a passage that clearly continues, but there's only about this much space between the ceiling and the water. And so you have to go through on your back and almost put your lips on the ceiling to get through, right? That's always a little hairy. And then after that, there was this crawl space that didn't look bad. It was dry. And then you get into it and realize that it just keeps compressing until you're really pinned down. And I crawled through. The first guy went through, and I crawled through, and he said, "Wow." I kind of started freaking out in the middle there, and it's like, "Did you?" I said, "Yeah," because at some point your brain says, "This is too small." And then our friend, right, the third man in line, starts to come through, and he's stockier than us, and he simply couldn't get through. So he had to actually back his way out because he was starting to get stuck.
Yeah.
So that's part of it, but I think over time you learn to navigate those situations, and you learn to appreciate the challenge of those situations. They can be exciting, but yeah, they're always a little bit. They should give you anxiety. If they don't, there's something wrong.
I'm of a nightmare now tonight, I think.
No, I've seen too many horror movies that involved in caves that nope. Descent. Uh.
Well, I think they're interesting spaces because, and I think you would think so too, potentially. I think they're interesting spaces because of we can access the past in a unique way in caves.
Yeah.
And especially these wild caves have their own ecosystems. They have these fascinating animals that live there and nowhere else. And so that's what gets me through it all and motivates me is this is so interesting. The things we get to see are so fascinating and special that it's worth the bad parts.
Yeah.
So have you found any evidence of human inhabitation or anything human related in any of the caves debris cones?
No, not in Inner Space Cavern. No. There was long a story about a human tooth, but we looked into that a little bit, and it was a peccary. So no, we were here, right? We're here at least 21,000 years ago in North America, and that's actually New Mexico. So we're close, if not here in Texas, 21,000 years ago. Why we don't encounter our own species in more of these caves, I'm not really sure, but we're different. We also deal with our kin and our relatives, our loved ones differently than most animals do. So that may be playing part of it. And we may just not have has been abundant either.
One question.
Go ahead.
One question concerning. I have a reverberation here.
You're all right. I still hear you.
Were these animals actually living in the cave, or is it the fact that there could have been a hole on the top that they fell in over various periods of time?
Yeah, great. I think
Now,
it's
granted, the bats would fly in and out,
right.
but peccary would just fall in and die.
Yes, right. The bats, right? The bats are perfectly willing to enter caves and leave caves and use caves as shelters. And they can navigate, right? Any sort of entryway. It doesn't matter if you can walk or not. Bats don't mind. Most of the other animals are species that, to the best of our knowledge, would never willingly enter a cave system, certainly not beyond the twilight zone, right? That interface between light and dark. Certainly, right? Mammoths, elephants, they do not. They are not willing to go into caves for the same reason we've just been talking about. They're uncomfortable. They can't see. Their senses don't work. So most of these animals are living and dying on the surface, and these sinkhole entrances into the cave provide a pathway, a connection for materials to move from the surface into the cave, materials like clay and rock and sticks and stone, but also animal bones. Then we have kind of a third category of animals that might have been willing to enter, like a peccary or a jaguar. But there it gets a little bit harder to tell if that's what they were actually doing or if they fell in or bits of their bodies fell in over time. Because we don't really know what the entrances, what the shape of the entrances were like and how these debris cones changed over time, right? They could have, during some intervals of time, made a nice little ramp, walkway, that you can just walk right into the cave, walk right back out, no problem. Maybe, maybe not. We can't see that, but what we can see are the fossil animals themselves. And in the case of the jaguars, the specimens, the fossils we have two nearly complete skeletons, which, right, a whole animal could fall into the cave, but it's also possible that that animal died in the cave. And it's the same thing with the peccaries. We generally encounter them as partial or complete skeletons. And so that also suggests these animals could have actually come in here and died here. But that's about as close as we can get to connecting the dots of how these bones actually got in. Pretty much all of the other species are represented by bits and pieces, like I was showing you, and that are consistent with those animals dying on the surface and those bits and pieces trickling in to the cave system where they could be kind of buried and preserved.
There's a cave system that has okay, I'll give it a try.
You got it.
There's a cave system up in Utah or something like that that has about an 8-foot diameter hole in the top that animals have fallen down into and made a cone. Is there a difference in the carbon dating between the bottom of that cone and the top of the cone, indicating that this hole has been there and just collected animals over the centuries?
I can't speak to the cave in Utah, but I can talk about Inner Space Cavern. And yes, yeah, there is a difference in the dates from the top to the bottom. And so we do have a mostly stratigraphically consistent sequence of dates, older ones at the bottom, younger ones on top, that indicate a actual chronology, an actual stratigraphy, an accumulation of materials, including fossils, through time.
If that's the case, and you had a quarry somewhere 50 or 500 or whatever yards away, it doesn't necessarily correlate with the age of where the fossil was and what the limestone age would indicate.
Yeah, absolutely. Yeah, these caves are all idiosyncratic and they're occurring at different levels in the limestone, and the fossils are accumulating in different parts of different caves. That's one of the fascinating things, is all of these caves serve as natural archives of natural history, but they're all utterly unique, and we can develop some general understanding of how they operate as time capsules. But each one is distinct and has its own stratigraphy, its own patterns, and we can't correlate, right, from one layer to another across geologic sections like we could with most geology.
So how
That would be
accessible?
indicative of animals falling into the cave then, as opposed to living in the cave and
Yes.
walking in.
Yes. For the most part, yes.
So how accessible are these caves to the general public? And are you still searching through different areas of the cave and still, going in there and digging and, obtaining more fossils and everything?
Inner space is very accessible to the public. As a tourist, right, you can see almost all of the cave if you're willing to experience all of the different aspects of the cave, right, which includes some crawling in spots. But I mean, a lot of the cave is a walking, well-lit tour, paved path. You have a guide, right? So I mean that's very accessible. And that goes for these show caves in the region. And there's some really terrific show caves like Inner Space Cavern in Central Texas, and they're very accessible. You really should go if you're down in the region. The wild caves, which I'm working in too, right, are not prepared for public access, and most of them you have to rappel into. And so, right, there's a real barrier to most people accessing these things. In inner space, I'm still working on the samples that I collected. I think I talked about how rich and diverse the fossil assemblages were, and that's not right. That's almost an understatement. Right? These fossil samples that I collected are providing me with fodder to write about and think about and to publish on for maybe the rest of my life. So there's really no end in sight in terms of these samples and my analysis of them. And those samples came from just 5 1-by-1 meter square excavation pits.
Wow.
And I was limited. I had an agreement with the landowners that I could only have 5 of those, and they could all only reach a maximum depth of 1 meter. So I could only have 5 cubic meters of sediment. And in most places, I didn't even achieve that because you run into a boulder or something and you can't keep excavating. So it's an enormous quantity of fossils for a very limited amount of excavation. And I really can't justify doing more, right? We addressed a lot of the major questions, or at least clarified it to a satisfactory extent. And there's so much material left for other questions, for other analyses, for more work, that I really don't have a reason to go back. And I think that's a really important thing to point out, and maybe to kind of wrap up on, that these sites are natural archives. They are irreplaceable. They are idiosyncratic. They record Earth history for us. Nature has recorded history for us in these things. And we can dig them up, but we should do it with purpose. We should do it with meaning. We should do it with intent, and we should do it when we need to, and not just because we want to go find more fossils. I want to find fossils more than anybody. But right, I know you guys know the feeling of trying to hold back and not keep going. But in some of these cases, we really should leave some of this material for future generations. It's important, and we don't know what they're going to be able to do, right? That we can't even imagine. 10, 20 years ago, nobody could imagine talking about those DNA methods that I mentioned. Who knows what we'll be able to do in the future, and we should leave as much of that archive for the future as we can.
Well, you're just leaving it on such a downer Debbie note for me, because I was going to ask for a bag of the dirt and sand from the bottom of the cave, and now I can't, because
I've got tons of
you
those
just
bags.
crushed me.
You come on down sometime. You can happily pick away and discover whatever tiny creature you want. Bags upon bags, believe me.
Oh, it was extraordinary. I enjoyed this presentation so much.
Me too.
Well, I'm really glad to hear it, you guys. That makes me happy, and means I was successful this evening. I really appreciate your interest and your time and having me out.
We're going to continue, but I think we're going to stop the recording now.
Yep.
But we can continue with questions. As long as you want to stay, you're more than welcome to stay. But thank you. Thank you so much.
Thank you all.
Yeah.
Thank you
Very
all.
good. Thank you.
Thanks,
Loved
guys.
it.